Hi, today our discussion will be about rectification that is controlled using thyristor. Remember, when you're using a diode, the diode you don't have control capabilities of the type of wave you need when using a diode, but thyristor provides that capabilities. The main difference between a diode and thyristor is a diode conducts the electric current once it is in forward biased. But thyristor, even if the thyristor is forward biased, it waits for gate current or signal current to be applied at the gate so that it can start conducting. I Basically, a thyristor it conducts when the gate receives a current trigger. It continues to conduct until the voltage across the device is reverse biased. Let me take a thyristor. Let me take both thyristors here and a diode. You can see the thyristor has a gate current. Diode doesn't have. Once you connect once you connect power to anode for the diode always allows the current to pass when in forward biased condition. That is when A is receiving current. But when you reverse, the diode doesn't. The thyristor and diode are the same, except now the thyristor has a control. Even if the thyristor is in forward biased, it will never conduct unless we trigger in G. But diode doesn't need triggering. Diode will always conduct in forward biased. It will never conduct in reverse biased. Thyristor will never conduct unless you provide a trigger at G. And once you provide trigger at G, G means gate, it continues conducting the electric current until it is reverse biased. Okay, therefore, I'm going to use the thyristor for the rectification and we are going to see the differences. Therefore, let me delete the diode. As usual, I don't need measuring port. Okay, we need now our voltage source. I went to source here, voltage source here. We always connect for the forward biased, always connect positive to anode, A for anode. And note, even if it is forward biased, the resistor will never conduct unless it receives signal at G. Therefore, let me now have a signal generator that will be used to control our thyristor. Let me show the name. Therefore, you go to library browser, go to Simulink sources. I need a pulse generator. Let me first illustrate a pulse generator so that you can be able to understand once we start using this with thyristor. This pulse enables us to generate a pulse that is defined in a pulse generator. Let me use a scope here very fast. In fact, let me first delete this. My focus will be here first. Let me go inside the pulse and have some parameters here. Amplitude, this is the maximum height of our pulse. For one complete period or one complete on and off is a period. One on, one off forms one complete cycle, that is a period. And the pulse width, this is the time the pulse is on. In this case, the pulse will be on, it will set a 1, assuming pulse generator is setting 1 for on and 0 for off. 1 represents 5% of the period. If I put 10% here, it means 1 second will be on and 9 seconds will be off. Okay, let's verify that. Let's run and see the scope. Let me like that maximize here. 1 second. You're using, remember, you're using 1 second here, but if you go inside the pulse generator, the period is 10. That's the reason why our scope is using just from 0 to 1. You can see sample based 1. Therefore, let me change this to 1 second, similar to our simulation time. 1 here, apply, okay, run again. Then we can, yeah, you can see it is on 1% of 99%. Okay, let me go back to, yeah, you're using a pulse width of 1%. Let me use 10% so that 0.1 second will be on, 0.9 second will be off. Okay, run. 0.1 second, that is 10% of 1 second. It is on. 1 is the maximum, that is the amplitude. Then the total time is 0 to 1. If I change here to 50%, it means my pulse will be on for at 50% of period, meaning 50% of 1 second. If I put 2 seconds instead, it means 50% of 2 is 1 second. Therefore, if you use 2 period here, you have to use 2 for your simulation. Run. Go back to scope. 1 second on, 1 second off. Therefore, that's how we use pulse generator. I'll be using this pulse to trigger a signal at G. Therefore, when this is high, when this is high, this one will start conducting if it is forward biased. If the resistor is forward biased and G is high from the pulse, the current will flow. Therefore, I need this one here to connect to G, and I'm going to use a frequency of 50. Let me use 230 SQRT of 2. For a frequency of sorry for that, we are seeing a frequency is 50 Hz. This means the period for one cycle is always 1 divided by frequency, that is 1 divided by 50, that is 0.02 seconds. And therefore, for 360 degrees, that is one complete cycle, will take 0.02 seconds. Hence, if I go back here, our period period is 0.02 because you're using a frequency of 50. This 50 is the frequency I defined in my voltage source 50 here. If you use 40, you have to use 40. You have to make sure that your pulse generator is synchronized with your power source. Then for now, I don't want any delay. Let's first put 0 degrees there. Just need a small signal, maybe of 5%, that is enough, just a small amount, because once you provide a small amount of G, a resistor starts conducting. I think that's enough explanation. Then I need load that is found at passive branch here. I need sensors. A current is supposed to be through the circuit. Like that. I need a scope. Let me monitor my pulse using the scope here. I need to monitor the current V in. In fact, you can use a go to. Check out my previous video whereby I explained how to use a go to. Yeah, I can rename this. This one is my pulse. This is the current. Can I make the scope bigger? No harm. This is V in. Make sure you select the signal. V in. This is V load. Like that. Then you go to scope, gear icon here. You need four layout, four of them. We need four of them. This is the pulse. Yeah. Let's see what happens. I just need 1 second here, simulation. Since our pulse is having a period of 0.02, that's okay. Yeah. Let's run and see what happens. Go to, yeah, good, perfect. Let me zoom in x-axis. As you can see now, my pulse is on, gets triggered just 5%, but nothing happens here. Nothing happens because there's no delay. Okay, this one starts, as you can see, the V load, the V out, that is the V out, the one we are trying to rectify, starts to rise at 0.02. At the same time, our pulse sends a signal to the thyristor. Therefore, selecting the thyristor at this point doesn't enable us to control our signal, our wave. How can you now control? Go back to pulse. We control the V load, that is the V out, using the pulse by delay. These three of them, they are just parameters to define our pulse. But the actual control happens when you input a delay value. Delay means it means that our V load will delay by a certain amount of time specified here. Let's now specify. Let's assume now we need this V load, the V out. We want to delay the 90 degrees section here. I want to cut it at this point and delay. I want to control. How can I do that now? You go back here. Remember I said the period is this is the time for the 360 leg. Therefore, 0.02 divided by 360, that is the time used by the V load to cover 1 degree. I need how many? I need 90. You multiply these ones by 90. It means that our output V load, our rectified curve, will be delayed by 90, by a quarter. Let's run. Let me zoom. You can see now when this one has a delay, it delays a little bit, then sends a signal. Therefore, my curve has to delay exactly 90. This 90 is eliminated. We eliminate 90 here because this one, before it becomes high, it delays by amount of time we have specified in pulse generator parameters. If I want to delay this one by 3/4 so that we can start our curve at this point around here, you have now to change the pulse from 90. If you need 3/4, you can put, let's start with 1. If you put 180, let's see what happens. You see, I'm getting nothing. Okay, because 180 is a complete half wave. Therefore, you have to use 90 plus 45, that is 135. We're going to get just a quarter of our V load curve. Okay. Now you are getting just a small section. This is a quarter. This one is similar to this, but now you are getting a small section here. That's how you use the thyristor to control your half wave rectification. Okay. Therefore, let me go back to our initial value. I want to use 90. You're going to use 90 throughout as we rectify both half wave and full wave. That is 90. Okay. Run. You go back here. You zoom. This is 90. But you can see we don't have anything on bottom side. Okay. Now, how can you now include a wave on bottom side. This is the top side, but we need bottom side. Okay, simple. We just need another thyristor to be in parallel to the first thyristor, but now our second thyristor has to be a reverse biased. If we select this, let's now move them a little bit to have more space. Another new thyristor, but you have to rotate it. This one is a forward biased thyristor, FB. This one is a reverse biased thyristor. This one, it will enable us to obtain the lower section, the negative side of our S sine wave. As usual, you connect A to that point, K to that point. You connect them in parallel. Then you have to provide a value at this point. Okay. Again, I take my pulse here, rotate it. You connect to G port. Just delete them. Oops. You connect them, but now this one is supposed to send a pulse after one complete cycle. Remember, not one complete cycle, half complete cycle, that is 180 degrees. Remember, the top is 180, bottom is 180, top is 180, bottom is 180. Therefore, this one has to wait until our sine wave has traveled exactly 180. Then at that moment, it has to wait and send a signal to our RB thyristor. Therefore, in this delay, then now if you don't change here, let's see what happens when you run. Let's see what happens here. Nothing happens. We don't get the bottom one. We don't get the curve we need because both generators are active at the same time. Therefore, if I was to take another signal here, you right click, let me select a go to. Let me put it here. Then we need 5 of them. Layout. Just select. Have to select 3, 6, like that, so that our last one will be displayed here. If you now run, okay, I said in my previous video, they should have different label. Therefore, I have to change this one to maybe B. Same applies here. You have to change tag for both. Otherwise, they are going to contradict. Where is our... You can see nothing happens here. Nothing happens. Our wave is still on one side. But now this one doesn't say anything. Therefore, I have to go back to the generator. You have to put remember for the 360 is this value, but we need 180 deg to be 0.01 seconds. Therefore, you have to delay this one here by 0.01, like that. This is the okay. You can see now we have Let me go to our vload. This is our main interest here. Let me go to the settings, go to automatic scaling so that you can get to the lower section. You can see now this one is setting, but now this one has a longer delay because it has to wait. This is my second pulse generator. It has to wait until this one has completed one half a cycle, that is 180. It has to wait, then trigger to allow the reverse biased thyristor to work. As you can see now, you have the first 90, delay another 90. This delay is 90. From this point to this point, if I was to remove this 90, yeah, let's see what happens if I was to remove that 90 and put just one. You see there's almost no delay. Therefore, the first 90 is now continuous with the bottom section. Okay, therefore I can now go back to how it was as you finalize 90, apply, okay, run, scope. This means that our pulse activates the top section. My second pulse activates the last section. This is the last section. Therefore, in my second video or my next video, I will illustrate now how you can combine everything to get a full wave rectification. Thank you for your time. Subscribe. Let's meet in my next video for a full wave rectification. Bye.